since I'm saying that, well, m hat's got to be smaller than m, let's do this trick. I'll say that m is equal to m hat plus some additional part, right? And if I have m converge onto m hat, everything goes to 0. Okay? And I can do the same thing for k. There's an optimal value plus some additional part that would make it non-optimal. Okay? The idea is that we're going to try to, not really so much take the limits, but get these n and z parts to go to 0, then we're at the optimal values. Okay, if I do that, the equation is quite messy, but it's a little bit simple. Being this mess. So what I can do is take this function, subtract it, so let's call this one equation 3, and this equation 4. Subtract 3 from 4. And what I end up with is a differential equation for m. Remember, our closed loop A matrix is A minus BK, which is A minus B, or optimal K plus this offset part, deviation. It may not be obvious, but this is the same form this expression. So it's the same form. And L and solution I can write this for and for n. N is a function of t, final integral from t to t, state transition matrix times L times state transition matrix. Now, if P is the minimum, letters there. That says that X transpose M hat X must be less than X transpose plus M X, or that. That implies that X transpose M is positive, definite, or at least semi-definite. It's got to be bigger than this. So if this is the optimal, it's equal to the optimal plus something that's bigger. That implies it's got to be at least positive, definite, positive, semi-definite. All right. So if you look at this equation for L, these bits, look at something here, is that if Z is sufficiently small, or Z is what we're modifying our gains with, and I'd like the Z to be 0. It means I'm at the optimal gain. So if Z is sufficiently small, the linear terms, these guys, these are not quadratic terms, these are linear terms. It's a quadratic term. Dominate C transpose by C. Basically, if this is well, these guys remain the first function. All right. And what it means is that if the linear terms disappear, we get to our optimal value. L is positive definite. We end up with the following. What says our optimal gains, K, are part inverse B transpose and this solution for M. So have to solve for that. Those will be the optimal values of K. Optimal feedback needs. So now I'm going to solve for M. That's not too trivial. We have a differential equation for M here. You put in everything. Use this form of it. Okay. And we put in K here. We put in the where K should be from that, we'll end up with this differential equation. We'll put in our function for K. This is known as Z Ricati, with 2 C's, 1 T. Italian. Don't get corrected by this by Italians. So if you ever hear anything called the Riccati equation, or optimal control in that equation, it is a nonlinear differential equation. Right? You can kind of solve it. There are some closed form solutions for it. Most of it has to be solved numerically. Okay? All right. Now, what's the case of, we can solve this expression, because notice it's all in terms of A, B, R's, and Q's, things that we know, we define. We can solve what this is, put it in, we have our optimal gains. So there's a simpler form we can use of this, and that is, what is it at steady state? What happens at steady state? Yeah.
Oh, I was just asking, in the third term in that equation, is one of those m hats supposed to be transposed?
No.
No, they're both okay.
They're both okay. So if it's steady state, what happens? Again, don't think too hard of this.
It goes to 0?
M dot goes to 0. Right. So at steady state, and this. This is known as the algebraic Riccati equation. That's what we'll typically use for regular. Algebraic Riccati equation. What's really nice is that MATLAB has this solution built in. It's called A-R-E, algebraic Riccati equation. They program this equation. It's not linear and everything, okay? But it's not terribly hard to solve. Okay. Certainly for most cases where I have a stable system, stable isolable system, if it's controllable and observable, this is always possible to do. There are cases if it's not controllable or not observable, to get solutions to this too. As long as what's called reachable. I'm not into the details, but we're going to try to make sure everything's controllable and observable. And we'll use that. Okay. Let's show how we can actually do this. Very simple example. Here. We'll do an example next time. Let's look at how do we define R and Q. Notice one thing here. R is inverted. That implies what? It's invertible. All right, what makes a matrix invertible? It's going to be square because they're also quadratics. So that's not a problem here. Well, remember Cambridge index. That says what about R here? It's going to be square because it's you transpose or U quadratic. If it's invertible, what? Must be the case. Determine not zero, which means it's full range, which also means it's positive definite. Or positive definite. Q, again, also should be positive, but it could be semi-definite. Semi-definite is what?
Greater than or equal to 0.
Yeah, it could be 0. I could put 0. But for R, that's the weighting function for our inputs. I've got to have some non-zero number there, otherwise I can't see the problem. Let's think about how can I, what's a nice way of defining what some of the problems are for these Q's and R's. First of all, let's take an example of X's position. X1 is position, X2 is velocity, and so forth. What about dimensions? X3 could be a voltage. X4 could be pressure. No, whatever our states are. Mixed up stuff here. What about dimensions here? Well, all of our dimensions are different here, right? I have different dimensions. But when all done here, this is a scalar. What is it? What's the dimension of V? It doesn't have to be.
It doesn't have one?
Yeah, it's dimensionless. These are going to end up in dimensionless. So I'm adding, essentially adding up, positions, velocities, voltages, whatever, maybe current here or something, but when some of them go up, then they're all kind of be dimensionless. Right? So that implies something about Q's and R's here. They must be what dimensions?
Inverse of it.
Inverse of the dimension squared.